Hello and welcome to the Applications of Electromagnetism in Transportation by Matthew Hahn. So firstly, all of these technologies are powered either by linear synchronous or linear induction motors. Linear induction motors are essentially an unraveled induction motor, so instead of providing torque, as shown here, the motor exerts a linear acceleration or deceleration. As seen in figure 1, induction motors work by having two parts, the stator and the rotor, where the rotor is the part which will move and the stator the part which is stationary. The stator is made up of copper coils and electromagnets, and the rotor is made of a conductive metal. When the stator is powered with electricity, it generates a travelling magnetic field, and this induces a current in the rotor, causing the rotor to generate its own magnetic field and causing it to interact with the field created by the stator, causing it to try and catch up to the stator's field, leading to thrust being applied on the motor. Linear synchronous motors work by having the rotor as a permanent magnet, producing a magnetic field. Then, the stator's electromagnets produce a magnetic field slightly offset to the field of the rotor. This causes the rotor to be both attracted and repelled by the stator, causing it to experience thrust in the direction the field is offset in. The offset of the magnetic field is constantly changing according to the velocity of the rotor to make sure that there is always an offset and therefore thrust, causing it to be a travelling magnetic field wave, as shown in figure 3. The advantages of these technologies are that they require no physical contact or friction to function, unlike the basic friction motor. This means that they require much less maintenance and are overall much more efficient. Furthermore, they are also very reliable. However, LIMs are less efficient than LSMs because some energy is lost as thermal energy to the surrounding environment. In large use cases, such as in roller coaster launches, LIMs can put strain on the electrical grid due to it requiring sudden bursts of high wattage electricity. With LSMs, the energy loss is minimal and it requires less spikes in energy to produce thrust. However, because of the complex nature of making sure that the magnetic fields of the stator and rotor are always offset by a certain distance, they are very advanced and are slightly more expensive to install. So one application of this technology is in roller coaster propulsion. Both LIMs and LSMs are used in launches to propel roller coaster trains to high speeds. For an LIM launch, the rotor is placed on the side of the trains as aluminium fins, as seen in figure 1 here. These are the aluminium fins. While two sets of linear stators are on either side of the thing on the launch track. If you just look here, these parts here underneath the ride platform are linear induction motors. There are two sets of them, one above and one below the aluminium fin. When the stators up here are powered with electricity, the train experiences thrust and accelerates off into the ride layout, as we explained earlier. Roller coasters powered with LIMs are rarer than ones powered with LSMs due to the inefficiency of LIMs, as they release much more thermal energy. LSMs, as seen here in figure 2, are also used for both propulsion and deceleration of trains, as the magnetic field can be offset in the other direction, causing the train to safely come to a stop when needed. Because they lose less thermal energy and are more efficient, the fact that they require less bursts of electricity, and because they provide both acceleration and deceleration, they are much more widely used for roller coasters. With the tallest and fastest roller coaster Falcon's flight in Saudi Arabia, which reaches heights of 534 feet and speeds of 155 miles per hour, being propelled by LSM technology. LIMs, while not as useful in roller coasters, have found to be incredibly useful for urban transport metro-like systems. These systems do not reach a high top speed due to type stop spacing, mainly accelerating and decelerating. Here, the stator, or primary, is placed on the train, while the rotor is placed on the fixed reaction rail, as seen here. So here is the here's the rotor, and here is the stator. When the stator on the train is powered, the induced current and force on the reaction rail propels the train forwards, as Newton's third law states that every force must have an equal and opposite reaction force, meaning that when a force is applied onto a reaction rail backwards, the train will be accelerated forwards due to Newton's third law. Applications of this technology have been installed on the Expo and Millennium lines of the SkyTrain in Vancouver, and in Guangzhou on Line 5 of the metro there, as well as in several other locations around the world. Now, both of these technologies are also used to propel maglev, short for magnetic levitation. There are two methods of creating a maglev train: electromagnetic suspension, EMS, or electrodynamic suspension, or EDS. In an EMS system, like the Transrapid Shanghai maglev, there are two sets of magnets: the levitation electromagnet here, which repel permanent magnets on the guideway, providing a layer of air between the train and the guideway, which leads to frictionless transport. Then the lateral guidance electromagnets and the reactor rail act as LIMs to propel the trains up to speeds of 501 km per hour or 311 miles per hour. This system has only been deployed at high speed on the 29 km long Shanghai maglev. For an EDS system at the Yamanashi test track in Japan, there are superconducting magnets on either side of the guideway, which provide both propulsion and levitation. However, the levitation here only works at a relatively high speed, and they need physical wheels to be stable at lower speeds, and they can reach up to speeds of up to 500 kilometers per hour. In conclusion, both LIM and LSM technologies are extremely useful for both low-speed and high-speed transportation. However, they are relatively expensive compared to more conventional methods and are much more technologically complex. They are currently at the forefront of technology and are continually being developed, with planned rollout of an EDS system between Tokyo and Nagoya in Japan currently under construction. Thank you for listening, and here are the citations for and sources.